to look at this event now and have at least a clear mind of what we are looking at, okay? So, number one, this type of graph will not be so helpful. Because as I said, it's easy to see Km, but it's very hard to figure out Vmax. Can be done, but you know, seeing all these curves going as a curve on the left and right, overlapping each other could be confusing. Instead, the double reciprocal plot that the Linear and Barth developed the years after, that might be helpful. It's basically a line like this. What happened is that we make the double reciprocal of the Michaelis-Menten equation. So it will be 1 divided with 0 equal to K Conem divided Vmax times 1 divided concentration of S plus 1 divided Vmax. All right? So just the reciprocal of everything. And what this graph identifies is just a very nice line. So there is a trade-off from that. The trade-off is that it's all reciprocal. So, for example, the intersect on the y-axis that identifies Vmax is actually 1 divided Vmax. So if the intersect is going to be closer to 0, Vmax is going to be higher, right? Similar things for the intersect on the x-axis. Actually, this time would be in the negative x-axis. In this case, it's 1 divided K Conem, which means that closer that intersect is to 0, lower is the affinity of an enzyme for the substrate, because higher will be the K Conem value. Bigger will be the value, smaller will be the K Conem factor itself, value itself, and higher will be the affinity. So, as a very simple suggestion, since these are kind of mind-twisting reciprocal behaviors, inverted behavior, it's always better to repeat in your mind before that you check an answer in an exam or say something. I can make mistakes right now because I know that plays funny with my head on those things. And if I'm thinking 3 things together, I might also say something wrong. But usually, if this is going closer to this point, this means higher Vmax, even though it is closer to 0. And if this one is closer to 0, it means lower affinity. So, what we can do with this? The slope is also identified K Conem divided Vmax, which is a we can use to study graphically how inhibitors of enzymatic reaction work. So this figure here represents all the types of inhibitors that can be out there. There is a very simple example that is the irreversible inhibitors or inactivators. For example, the classical example for that is aspirin. Aspirin is an irreversible inhibitor or inactivator. On the other side, there is the reversible inhibitors. Example, ibuprofen, for instance. It's funny because either ibuprofen and aspirin work on the same enzyme, but they behave in a slightly different way. Aspirin is acetylating a subunit enzyme, so it's like affecting the overall enzyme, killing it. The ibuprofen, even though the mechanism is not completely clear, blocks the enzymatic reaction, but could be outcompete if you put more substance. So, of the reversible inhibition, there is that one that affects the catalytic activity, or those that affect substrate binding. Those one, in the case of ibuprofen, is a competitive inhibition. That one that affects the catalytic activity is the uncompetitive inhibition. Don't mix that up with the non-competitive, that is another thing. And then, if there is both of them acting together, there is the mixed inhibition. So it's a little bit competitive, a little bit uncompetitive. So this graphical representation will blow up in the rest of today's lecture plus the next lecture in an interesting way. The aspirin example or the ibuprofen example require us to go and recall one slide that I showed you during lipid studies. Is that one that showed how arachidonic acid is on top of the molecule from which many other molecules are formed, for example, prostaglandins, thromboxanes, prostacyclins, lipoxin, okay? Prostaglandins are mediators of inflammation, fever. Those are synthesized when we have an infection and we get the fever. The fever is a reaction of our body to that infection, to try to get rid of it. So, pain, similar way. So, we call that enzyme here, the first enzyme PGH2 synthase. A more common way to call that enzyme is COX-1 and COX-2. And they do slightly different things. Some of them, like COX-2, is more involved in prostaglandin formation, while COX-1 is more involved in thromboxane and prostacyclin effects. However, both aspirin and ibuprofen are not selective, so they cannot recognize between COX-1 and COX-2, inhibits both. Sometimes even a little bit more COX-1. This is why we get inflammation and bleeding if we don't eat. I know my accent is funny, but if you continue, you are invited to go out. Okay? Because it's disturbing me and everybody else. All right. So, where I was. Okay. Next lecture, I will show you also what happened a few years ago when Merck decided to create a new molecule that was selective for COX-2. And they almost went to bankruptcy because that molecule was actually killing me. So, in terms of competitive inhibition, what is relevant is the fact that some examples are relative to molecules that are completely not natural, or if they are natural, they belong to defense systems. So like for substrate analogs or transition state analogs, those are molecules that we make in the lab just to block an enzyme, to make a drug, or to make crystallographic studies. Or if there is an animal or a plant that creates that to block something for its own defense. Okay? While there is a physiological process that is connected with this type of inhibition, and that is when a reaction produces a product, so enzymatic reaction produces a product, which product is also has some form of affinity to the substrate, to the enzyme. So that could be a form of regulation of the reaction itself. So this will be the example. So in the case of a competitive inhibition, look at this first. And the reaction, a normal reaction is like this, like we have seen many times. But what happens is that there is also an inhibitor here that can sit exactly where the substrate sits. So can take the space and the substrate is taken out. So when is this case, we can add here like an inhibitor, a Ki, which is the dissociation constant, producing Ai plus the substrate and no reaction left. Ki is calculated in this way. And the value of Ki is determinant. Because if it's too high or too low, with relationship with the Ks at least, or Kn on this regular reaction, and we will see how much substrate can really bind or how much inhibitor can bind that enzyme. So, an example that is happening in one of the most important steps of a citric acid cycle is the formation of fumarate from succinate. This reaction, succinate dehydrogenase, can be blocked by malonate, which mimics the substrate. Another example is, and this is more physiological, we'll do more about this, is the transformation of adenosine into inosine. Inosine has also affinity, which is the product, has also affinity for the enzyme, and if inosine is building up, can go and bind the enzyme instead of the adenosine, which is the substrate, the classical substrate, blocking that reaction. That means modulating the enzyme activity. Quick example. We just put some number for Ki. There is two examples. Km here is 10 powers to minus 5, and the Ki at this level is either 10 powers to minus 3 molar or 10 powers to minus 7 molar. Which one of the two types, potential types of inhibitor is more dangerous? That one that has 10 powers to minus 3, or that one that has 10 powers to minus 7 as Ki?
So minus 3, just move a lower amount of the inhibition.
What is a smaller number? Minus 3 or minus 7?
I would say like the minus 3 would be more potent compound.
What is a smaller number? 10 powers to minus 3 or 10 powers to minus 7?
It's like a 7. That's
So which one is more dangerous?
so that's the next.
Going back to Kekoman, the same is from the other. Ki could be considered something of similar to Kekoman or Ks. Smaller is Kekoman, higher is the affinity. So smaller is also Ki, higher would be the affinity of the inhibitor to the substrate, to the enzyme. Okay? So it's 10 to the power to minus 7.
Yeah, it's very large magnitude of smallness.
That is why the example is there, to make you guys understanding that it's good to think about it, think through every single thing. All right, so that is the guy that will stop largely this reaction because it has higher affinity than S. While this one will still stop the reaction, but with lower affinity, so we'll slow down a little bit, but not as the one with 10 powers to minus 7. Uncompetitive inhibition. Now the inhibitor doesn't necessarily need to bind the binding site of the substrate. It can bind nearby, or even the catalytic site if it's not the same place. When it does that, it's stopping the reaction. So this means that doesn't matter if the substrate and the enzyme are already binding each other or are not, but they could still bind each other because once that happens, the reaction is anyhow stopped. So now we represent that in this way. It's from ES plus I that produce ESI. This is K prime I, the dissociation dissociation constant of this reaction, and this is the way to calculate. Okay? We will see some funny things about this next lecture. Really interesting. And finally is when we have the mixed inhibition. Mixed inhibition would be when there would be the same inhibitor. Actually, this part here is not present there, so I cancel. will see that next lecture eventually. But either combine an inhibitor before the substrate or after the substrate, the result is the same. So it will be either competitive or uncompetitive. And these are the two cases involved. So be sure that you review these because next lecture we can review the specifics of all them with all the data. Your mind over at least how the technical and science work. Review the study guide with the